Capital Gate, the most inclined tower in the world. In response to Sheikh Sultan's request to build an impossible architecture, designers came up with a tilt design inspired by the winds and waves of Abu Dhabi. Sultan liked the design of this building, but the constructor expressed a disapproval to the design. This building was tilted almost 18 degrees. Considering that the world's most tilted building had a record of 10 degrees before this, it was a great adventure to construct such a building like this. In order to construct a building, constructors had to try various construction methods that were different from the existing construction methods, from the foundation of the building to the cores, and transferring materials. In the previous presentation, we ended up talking about how the foundations of this building were made and what methods were used to make the core. Starting from this week, we are going to talk about one of the most important issues of this building. What makes Capital Gate Tower one of the most iconic buildings on Earth? It is the lean and the twist. We have explained how the tower sustains its weight due to the lean in the past presentation. Now, we are going to talk about the twist. What makes the tower's external form look twisted? What helps the building realize the twist? It is the diagrid. A diagrid is literally steel beams formed in diamond shaped. It is a new system used in the construction of large buildings, which creates a skeleton composed of triangular structures and diagonal support beams, using less steel than a typical steel frame building. However, because it requires hard work with extreme difficulty, there are very few buildings that use this diagrid structure, almost under 40 buildings in the world. Then, why did Capital Gate Tower need to use this high-quality technique on its outer form? The first main reason was to fulfill the design requirements of the Sultan, as he wanted a lean building that could break the common sense of architecture. It was inappropriate to use traditional load-bearing like columns. It needed some other method to resist the lean load without spoiling the beauty of the tower. So, the diagrid was the only way to accomplish the job. It eliminates the need for large corner columns, allowing more flexibility in the shape of the building's form. The second reason is that diagrids are the excellent solution for resisting lateral loads. Putting our site in consideration, Capital Gate Tower had to be able to resist the strong wind forces of Abu Dhabi. Capital Gate Tower could solve this problem in an architectural and structural perspective. With the curved external appearance, the tower could disperse the wind, and the diagrid could handle the wind structurally. Based on truss structure, the triangular unit can not only resist vertical load like the core, but also transfers the subjected lateral load to the member below. This also helps resist the lateral load of the overhang. Putting these two reasons together, the diagrid system was chosen to help realize the unique architectural form of the building. This diagrid is actually a result inspired by the eggshells. Even with a very thin layer of eggshells, eggs can withstand huge loads because it evenly distributes forces down through its shell, which means the shell can be thin, allowing more space inside. Steel beams connect to a load or joint to form a crucial form sections of 720 uniquely shaped sections linked together to form the thin but immensely strong diagram. These cruciforms work together to equally distribute the forces down the outside of the building. So, to make this twisting, leaning design, the diagrid had to be turned from theory to reality. But starting from the construction, the constructors faced serious problems to realize the complex and almost impossible diagrid form in this twisted shape. The problem was that they had to fulfill both the designer's needs and the structural engineer's responsibility to secure the stability. If it were a normal standard building, they could use the same diagrid with uniform size and angle, but to realize the twist, it was indispensable to use all different diagrids with its unique geometric shape. As you may guess, it would be even harder to connect these unique shapes into one whole mesh. However, in structural terms, if the diagrid is not assembled with millimeter accuracy, the mesh will not channel the loads and the structure could be weakened. The diagrid would not be able to perform its roles as the load-bearing device, and its principle would become meaningless. It was yet again a stressful challenge to the engineers constructing the diagrid, and no mistakes were tolerated. So, how did they do it? Because each of the diagrid members were different and had to bear different loads, engineers must communicate closely with the expert steel fabricators. Different with other towers, Capital Gate Tower's revolutionary design pushed even these experts to the limit. Project engineer Bhaskaran and his team need bespoke 3D software to tackle the building's highly complex diagrid. It helps to clearly identify any unforeseen criticalities. For the design part, the members were oriented with minimal offset by adopting the method of bisection of bisecting planes. This means they cut the diagrids into two equal or congruent parts, usually by a line, which is then called a bisector. These offset values were taken from the Teklar 3D model and used in the design of cruciform nodes. Beams connected to the nodes were moved in the model to avoid member clashing, which could result in eccentric connections. The eccentricity was measured from the model and used in the connection design. All the members had colors that show their usage and position. After they calculated and designed each members, they gave reports to site that showed location of center of gravity and weight of individual assembly. These reports helped the rigging team working at the site to erect the diagrid assemblies at their exact position and steel fabrication team to make different cruciform. Through the information of BIM, they found out that the lowest part of the capital gate receives the most load. Calculating and defining each load in each layer of the building, which gradually lowers up as it goes up. Therefore, they could use more thin steel members in places with less load. So, each external diagrid's thickness varies from 80 mm to 40 mm on the top floor as it rises from the base of the building. Additionally, thinner steel members meant that the proportion of glass would increase, and this was another advantage to emphasize the twisting shape. With BIM, they could also precisely predict each unique cruciform's detailed length, curvature, and each different form of nodes to connect them. With these reports, they were able to make each 720 designed cruciform that neither one were the same. They had to make it precisely So engineers used an old school method, chalk, to mark and calculate exact angles. It might look unsophisticated that they draw plans on the ground with rulers and protractors by themselves, but it's highly accurate, ensuring that all the elements are to be joined together. So first they connected each members fitted on the chalk drawn by contractor at specific angle. After that they chalk on each end of crucial form to make unique nose. In these processes, they could make each unique cruciform that could realize the twisting design. What was left for them was to accurately assemble the unique forms to create a uniform net for the load. 18 cruciforms were transferred to site every week. When they started to assemble those, each 16 tons of cruciform were lifted from the ground using the crane. And location of center of gravity and weight of individual parts were used to work out the lifting method and in the design of erection engineering. When it was lifted to the precise angle to match the opposite side of the endpoint, a team of 240 steel fabricators assembled the diagrid with nose and welded all three together. They had built straight part of capital gate's base easier, but when the structure is starting to lean, installation of cruciform were even more challenging. As the tower reaches new heights, the longer hours to pay off. But they needed to finish their construction in a short term. A lot of people worked all day, 24 hours, which pushed teams at a limit. This week, we talk about focusing on the diagrid, how to diagrid to work in the capital gate, and how to make and install the diagrid on the capital gate tower. Next week, we will talk about glass attached on the diagrid. Thank you.